say go and visit GCSE Pod, watch some videos, do some assignments on there, great website, good for revision. Okay, 9b vector diagrams. The first thing that you have to be able to do or identify is what's called a free body force diagram. So, by definition, a free body force diagram is a diagram that only has the forces acting on one object. Okay, for example, if you have an apple on the table, then you might draw the weight of the apple down and the normal contact force upwards, which is the force from the table on the apple. Both of those forces are forces on the apple only. Okay, so that is a free body force diagram. However, if we draw an alternative diagram, same thing, apple on table, you can have a normal contact force, which is the force from the table acting on the apple, but you may also see a force labelled force from the apple on the table. Now that's an action-reaction pair, so that actually does count towards Newton's third law. So it is correct for Newton's third if you say force from apple on table, and the reaction would be the force from the table on the apple or the normal contact force. That is Newton's third law, that's the action-reaction. But it's not a free body force diagram because those forces are acting on two different objects. Okay? Now the alternative is for a free body force diagram, weight down, which is force on the apple, and normal contact force up, which is also a force from the table on the apple. So it is a free body force diagram, but it isn't Newton's third law, because the weight of the apple is a force from the earth on the apple, and in Newton's third law, the action-reaction has to be between the same two objects, but in the opposite direction. So it would be the force from the apple on the earth. Okay? So it is a free body force diagram, but this is not action-reaction for Newton's third law. Whereas this one is not a free body force diagram, but it is Newton's third law action-reaction. Okay? Moving on. The next thing that we have to do is literally to determine what the resultant force is using vector diagrams. We have two components perpendicular to one another. So the first vector diagram or scale diagram that you'll have to draw is when two forces are perpendicular to one another. Okay? So the first one we have is 500 newtons to the right, 250 newtons up. What we need to do is we're going to draw the resultant force, which we know is between them. So first and foremost, make sure when you're drawing your vector diagram or your scale diagram, you think before you draw it, where should my resultant force be? Okay? Because you know for a fact the resultant on this object here between those two forces is going to be somewhere in between here, closer to the 500 than the 250, but it will be in this direction. So when you finish your diagram, if your resultant force is not in that direction, you've done something wrong. The size might be okay, but the direction will be wrong. First thing we need to do is create a scale. So for 250 newtons and 500 newtons, let's go for 1 centimetre equals 100 newtons. That will give us, for this one, a 2.5 centimetre line, and for this one, a 5 centimetre line. That's probably just on the borderline of being too small, because if your scale diagram is too small, when you draw your resultant force to scale, and then you convert back into a force, you will probably actually lose quite a lot of accuracy because your diagram is so small. So the bigger a scale diagram is, the better and more accurate it's going to be. So this one we're going 1 centimetre equals 100 newtons. So like I said, vertical force is 2.5 centimetres from 250, and the horizontal force is 5 centimetres from the 500. What I need to do now, again, I know the resultant is between here somewhere, so I know that it's going to be a line in this direction, but how do I find that resultant line? I need to complete the shape. Now what that means is, if the lines are perpendicular, the shape that would make is a rectangle. So if I just draw around the tips of the force arrows, it's going to be a rectangle for perpendicular forces. It could be a square if it was the same size, but it will always be a rectangle or a square for perpendicular forces. So complete the shape. I always draw it with dotted lines just so I know they're not the actual forces. And remember, the resultant force is corner to corner, but I know that it's this corner to this corner because it should be in that direction. So if I join corner to corner, that is my resultant force. Now what I need to do with my ruler is measure from this corner to this corner, get the value of this force in centimetres, which I know has to be bigger than the biggest component. So it cannot be less than 5. So it would be, let's say, 5.5 centimetres, and then I convert it back by timesing by the scale that I chose in newtons. So this is, if this is 5.5 centimetres, times it by 100 is 550 newtons. That's my resultant force. If I wanted a direction, I just get my protractor, put it on here, and I'd maybe measure this angle, or even this one here, and then I know exactly the direction. But I know it's going to be closer to the 500 than it is the 250 because it's bigger. Alright? So there's how you draw a scale diagram to find the resultant force from two perpendicular forces. Another example, we could have 1,000 newtons down, 600 newtons to the right. Choose a scale. So 1 centimeter, let's go for 200 newtons. That means downwards, if I start from this point here, downwards is going to be 5 centimeters, and across is going to be 3 centimeters. What do? Complete the shape. So again, it's a rectangle because they're perpendicular. Where do I expect the resultant force to be? It's this way. If this is an object with those two forces acting on it, I know that it's going to move in this direction, but it will be closer to the 1,000. So I go from this corner to this corner, measure that resultant force with my ruler, and then multiply it again. It has to be bigger than 5 centimeters. Let's call it 5.5 centimeters again. And then this time I multiply that by 200. So it would be 1,100 newtons. Alright, which makes sense because it's bigger than my biggest component. Alright, so that is a scale or vector diagram to find the resultant force when you have two perpendicular component forces. Alright, this can change. So if we go up here, you have forces at an angle, and it specifically says here, draw a parallelogram. So far our resultant force, our scale diagram, was two components with a rectangle drawn around it. But if the forces are at an angle to one another, then I'm going to have to draw a parallelogram, okay, every single time. An example, 350 newtons to the right, 200 newtons up, but it's at an angle of 20 degrees to the vertical. So the angle between those two forces is actually, if I draw the forces back to the center of the object, the angle between them is going to be 70 degrees, okay? Choose a scale. 200 newtons and 350, I went for 1 centimeter equals 50 newtons. Okay, so get rid of that. I start from the center again. The easiest one to draw will be the horizontal one. So 350 is going to be 7 centimeters. And this one, I need a protractor. If I'm going to draw a parallelogram with angles between them, I'm going to need a protractor. So 70 degrees with my protractor. And then this one will be 4 centimeters, okay? So there's the diagram I start with. I chose my scale. I converted that 350 on a scale of 1 centimeter is 50 to 7 centimeters. 200 newtons would be 4. And I had to use my protractor to draw the 70-degree angle between them, okay? All I need to do now is take this one, or maybe this one is the easiest again, because it's horizontal. Draw a 7 centimeter line on the top of there, and then just join them up, and there's my parallelogram, okay? Remember, it's going to be between the two, so it's somewhere in that direction. So it's this corner to this corner. There's my resultant force. Take my ruler, measure the line. I know it has to be bigger than 7. Again, you don't know what it's going to be. The bigger your diagram is, the more accurate that your value will be before you convert it back. So again, just bear in mind, the scale you choose, try not to go less than 2 centimeters. I'd say anything less than 2 centimeters is going to be very difficult to get accurate. And then measure corner to corner. Look where you think it should be, and make sure you follow the same and the correct corner to corner. Measure with a ruler, and then convert by times it by 50 newtons. All right? Another example of this again. We've got a 500 Newton force vertically up. We have 300 newtons, which is slightly inclined to the horizontal, 30 degrees above. Again, the angle between them is not 30. The angle between them is actually 60 degrees. So choose a scale. 1 centimeter here could be, let's go 100 newtons. Means this force vertically up is going to be 5 centimeters. Take my protractor. I need 60 degrees between them, so I go 60 degrees. And 300 newtons is 3 centimeters. There's my scale diagram. Because there is an angle between them, and it's not 90 degrees, it's going to be a parallelogram. So take my 5 centimeter line, which is vertical, that's the easiest one to copy. Go 5 centimeters, and then with your ruler join the tips. There's my parallelogram, and again, I know it's somewhere in between them, so it's this corner to this corner. Measure that resultant force with a ruler, times it by the 100 scale in this case, and then that's my resultant force between two forces, not at right angles. The very last thing you could be asked to do in vector diagrams is the opposite process of what we did for two components that are perpendicular to find the resultant. We could actually be given the resultant force and be asked to go back and find the components. So, here's an example of a resultant force. Let's say it is 500 newtons. This is only one force. So if this were an object, for example, a box on the floor, and there was one force acting on it at an angle of 40 degrees and it was 500 newtons, this object is going to move in that direction. There are no other forces acting on this object, so this object will move in the direction of the resultant force 500 newtons. But if I want to know where are the components, because part of this object is going to move to the right, and part of the object is going to move up, because it's moving up and right. So any force that acts at an angle, so one single force that acts at an angle to the horizontal or an angle to the vertical, has two perpendicular components. One of the components is horizontal, one of the components is vertical. So if you're dragging this box along the floor with a force at this angle, some of your 500 is going into dragging it along the floor, but actually some of your 500, a component of your 500, is going into pulling it up as well. You may not want that, but that's the situation. So if you wanted, for example, to make all your 500 newtons go into just pulling the box along the floor, you'd have to pull the force, you have to go lower and pull the force perfectly horizontal, and if you wanted to lift it vertically up, then you'd have to pull the force vertically up. Now, if I want to find the sizes of the components, so what component of my 500 newtons is actually pulling this box along the floor, along the horizontal, I have to draw a scale diagram again. So for 500, I'm going to go 1 centimeter equals 100 newtons again. And then the exam, they might actually give you a scale, so use the one they give you. If not, choose one that's appropriate. And I'm going to start, I need a protractor, or they would give me this line again. They may actually set it up for you, you just have to go around it, but if not, you'll be prepared. 40 degrees above the horizontal, 100 newtons is 5 centimeters, so I'm going to draw a 5 centimeter line at 40 degrees. Then all I do, if you have a resultant and you need to find the two components, it will always be a rectangle. So the two components will always be perpendicular, and it will always be a rectangle. So what we do is we draw around the resultant force a rectangle, and the two components are here, horizontal, and here, vertical, so call that H and V. And you get your ruler, you measure the horizontal component, times it by 100 to convert back to a force, and you measure your vertical component, times it by 100 to go back to the force. Okay? Final example then. Same again. This is clearly a resultant force because there are no other forces acting on the object. So if I have the resultant force, all I need to do is choose a scale. In this case, 200 newtons, I've gone for 20 is 1 centimeter. It's 15 degrees above the horizontal. So if they didn't give it me, I get my protractor and I draw my line. 20 newtons per centimeter is going to be a 10 centimeter. This is quite a long line. So 10 centimeters, and the angle was 15. And again, all I do is draw a rectangle around the resultant, and the two components are vertical and horizontal. Measure the horizontal, measure the vertical, unless they just ask for one, in which case you just measure the one they want, and times it by 20 to turn it back into a force. Okay, and that's it.